All right, so we've done a fair bit of work. Really, the majority of the work was just to be able to understand and talk about the central limit theorem. Um, why do we care so much about the central limit theorem? Because the central limit theorem kind of powers the two main types of statistical inferences that you as a statistician will practice day in and day out. And those two very common types of statistical inference are A, confidence intervals, and B, hypothesis testing. So this PowerPoint and the next PowerPoint are going to be focused solely on confidence intervals, and then the next, whatever it is, 2 or 3 PowerPoints that come after that will focus on hypothesis testing. So confidence intervals can be made for any range of confidence. So you have these percent confidence intervals. In theory, they could be any percent between 0 and 100, although in practice, they're almost always 95%. So in practice, we will almost always make these things called 95% confidence intervals. That's what, say, our government mandates, what the FDA mandates. So I guess we decide if it's good enough for the government, it's good enough for us. Now, confidence intervals, what they basically do is they specify a range of plausible or possible values for some population parameter, for example, the population mean. And they do this by taking the best guess, right, which is a statistic. It's in the example we just talked about, be the sample mean, and tacking onto that some sort of margin of error. Right, so it's a very, I think, simple and intuitive idea. We've said already that the sample mean is a good best guess for the population mean. Why? Well, because it's very likely to be very close. Now, the sample mean is not going to dead on be the true mean. It's in fact, the probability of that happening is 0. But as we said, it's very likely to be very close. So what we want to do is we want to be able to quantify this idea of closeness. We talked a little bit about doing that in the previous PowerPoint, but that was a little bit of a haphazard approach. Confidence intervals are a little bit more directed, although they do a very sort of similar thing. The whole goal of confidence intervals is to tell us, right, how close we think our sample mean is to the true mean for a particular level of confidence, as I said, typically 95%. So let's go ahead and take a look. Now, the margin of error that I talked about is generally a certain number of standard deviations of the statistic. The standard deviation of a statistic, sort of sidebar or side definition, is called its standard error. So a certain number of standard errors. Now, how many standard errors we want to sort of go out, how many standard errors that margin of error is, depends on how confident we want to be. The more confident we want to be, the sort of further out we have to go to accommodate that confidence. Now, a C% confidence interval, so for sort of any confidence level C, for some unknown population mean, when we know what the population standard deviation is our best guess, x bar, plus or minus our margin of error. Now, our margin of error is that z sub c. That z sub c is a critical value. It's got that subscript c because it depends upon how confident we want to be. That second quantity, sigma over the square root of n, well, remember, sigma over the square root of n is just what? It's just a standard deviation of x bar, isn't it? Thanks, central limit theorem. So we're going a certain number of standard deviations out. How many standard deviations? Well, it's that critical value, that z sub c. And as I mentioned, it depends upon how confident we want to be. Now, how do we find z sub c? How do we find these critical values? Well, the critical value for a given confidence level, say 95%, is the value from a standard normal curve such that 95% of the area is between negative z and positive z. The sort of intuition for why that is something you will explore in Stat 506, I think, when you talk about these kind of pivot approach to confidence intervals. But for now, maybe just sort of take my word that that's how it works. So the critical value for, say, 95% is the value such that 95% is between it and its negative value. Now, for 95%, this corresponds to 1.96. I don't want you to memorize that. I don't want you to take my word for it. I want you to go back to the tables that we had a few PowerPoints back. I want you to pull those tables out. I want you to draw some pictures. I want you to think about how to do this yourself. At this point, you should have done enough practice problems and internalized this enough yourself that you can kind of on your own way show yourself that this value is 1.96. Look at the table, think on it, draw the picture, meditate, and do not rest until you know why it's 1.96. And if you cannot figure out why it's 1.96, then you should come talk to me in my office hours, or hey, even before class or during lab, or talk to one of our graduate assistants. Now, it turns out more generally, the critical value for a C percent, I know this formula looks a little bit crazy, but it's not too bad, is 1 minus the quantity of 1 minus C divided by 2%, percentile of the standard normal curve. So if we're talking about 95% confidence, we'll plug 95 in there. So 1 minus 95 is I guess maybe it should be 0.95. So 1 minus 0.95 is 0.05. 0.05 divided by 2 is 0.025. 1 minus 0.025 is 97.5%, right? So it turns out the critical value for a 95% confidence interval is the same as the 97.5th percentile of a standard normal distribution. The percentile is the value such that 97.5% of the area is to the left of that value. Again, this statement really should make sense to you if you've been doing all the practice problems and you've been building up the sort of visual intuition for how all these different areas kind of work and come into play. And it's kind of bigger picture concepts like this, which is why I was encouraging you to put in the work earlier. You should be able to convince yourself about what I said just there, that the critical value for a 95% confidence interval is the same as the 97.5th percentile of a standard normal distribution. Again, if you do not understand that, you need to come talk to me. You need to come talk to some of the GAs. Some other common critical values, 95% is pretty much all that's ever used, but just for you to get a little bit of extra practice, the critical value for an 80% confidence interval is 1.28. The critical value for a 90% confidence interval is 1.645. The critical value for a 98% confidence interval would be 2.33. Pull out your table and verify these numbers. Again, do not memorize them. Do not take my word for them. Derive them yourself as if you did not know what they were. Incidentally, to sort of reinforce what I talked about in the previous slide, the critical value for 80% confidence corresponds to the 90th percentile. The critical value for 90% confidence corresponds to the 95th percentile. And the critical value for 98% confidence corresponds to what percentile? Ah, good job, you're right. It corresponds to the 99th percentile. We could actually find percentiles in SAS fairly easily. So we use something called the probit function. The probit function will return percentiles from a standard normal distribution. So if you use answer equals probit 0.975, of course you have to do that within a data step, and then you do a proc print, you'll get the value 1.96. So 1.96 is the critical value for a 95% confidence interval, which again, remember we said corresponds to the 97.5th percentile of a standard normal distribution. In R, we can find percentiles using the qnorm function. So the qnorm function takes 3 different inputs. The p is the percentile that we want, and then you could do the mean, so you can do it for any mean, and you could also do it for any standard deviation. Now, right, in particular for confidence intervals, we're looking at a standard normal, so that's a mean of 0 and a standard deviation of 1, so we would put qnorm 0.97501, and then try it for yourself. You should get 1.96 back at you from R. So just a kind of quick, easy example. Say that we want to know the average jumping distance of kangaroos. I mean, who wouldn't want to know that? And of course, what would we have to do? If we really wanted to know it, we would have to take a sample, right? So we go on kangaroos.com. We order, let's say, as many kangaroos as we can afford. Turns out that 64 kangaroos are on sale. We line them all up in our front yard. We have a kangaroo jumping Olympics. Let's go to town. Every kangaroo jumps. We record how far it jumps, and we look at the average jumping distance. So the average jumping distance for our sample of kangaroos is 25 feet. But what we're interested in is the average jumping distance of all kangaroos. Now, one final fact, everyone knows, of course, common knowledge. I can't remember if it's 2nd grade or 3rd grade, but right, we've all learned that the population standard deviation jumping distance for kangaroos, that sigma is 4 feet. I'm pretty sure that's common knowledge. So let's go ahead. I know 90% is a little quirky, but let's do a 90% confidence interval for the true but unknown mean jumping distance for all kangaroos. Well, it's really just plug and chug, right? So that formula that we saw previously, we kind of already said, and you verified and proved and convinced yourself that the critical value for 90% confidence is 1.645. So we just take all the numbers and we plug them into the formula, right? So our x bar was 25. We said our sigma was 4. Our sample size, we had 64 kangaroos. Critical value for 90% is 1.645. Plug all that in. We get 25 plus or minus 0.8225. So that 0.8225, it's our margin of error. So our confidence interval is 25 minus that to 25 plus that. So our confidence interval ranges from 24.1775 to 25.8225. So we would say what? We would say that we are 90% confident that the true but unknown mean jumping distance of all kangaroos is somewhere between 24.1775 feet and 25.8225 feet. Yeah, pretty easy, right? And fun. Stop. At this point, I want you to do section 8.1 from the practice problems 3 before continuing onwards. Perfect these confidence intervals, do them and do them and do them, and along the way, I mean, what is probably one of the truest mottos in the world, right? Practice makes perfect. So if you want perfection, you have to put in the practice. So hop to it. Little kangaroo pun.